Welcome to the course on Compressible Flow. My name is S. Ramaswami and I'll be your teacher. In this video, I intend to give you an overview of the course. At the start of any course, I would have 4 questions. First, what will we learn? Next, what books should we read? And what other resources can we use? And by the end of this course, what will we understand? We'll start by reviewing what we learned in earlier courses on both thermodynamics and fluid mechanics. We remember learning about a property called entropy and about treating a process as isentropic. We will see when it is reasonable to assume an isentropic process. We've also learned about an ideal gas law. In this course, we will not say ideal gas, we will say perfect gas. And we will take the more nuanced view of what we mean by that. Also, it would simplify our work greatly if we could regard a flow as one-dimensional. So, first question, when can we do such a thing? And second question, how do we simplify our work? What happens to the equations for conservation of mass, of momentum, and of energy? Also, there is a parameter which we may have simply defined in a first fluid mechanics course, the Mach number. We are going to see that the Mach number is as important in compressible flow as the Reynolds number is in incompressible flow. Next, we will learn about a special kind of wave called a shock wave. In short, a shock wave represents an extremely fast compression of a fluid. So fast that we don't treat it as a continuous process, we treat it as a jump. A shock wave is generated when a supersonic flow meets an obstacle, like say a round-nosed object. The bow shape you see in the center of the screen is called a bow shock wave. M of course stands for the Mach number. To keep it simple, we'll look at a very small part of such a shock wave. So small that we could treat the shock wave as straight. We may readily see that depending on where we look, that shock wave may be perpendicular or normal to the flow, or it may be oblique to the flow. And we will ask ourselves, how does the flow change across the shock wave? At this point, we may ask, the shock wave that's generated near a solid surface, sometimes at a surface, could very well meet another solid surface. In which case, how does the flow change after the wave has met the wall? For that matter, what if 2 shock waves are generated at different solid surfaces and they happen to meet? We will address that question too. So, we will also learn about expansion waves, starting with the question of how an expansion wave is generated, to which the short answer is a supersonic flow is induced to turn outwards, so to speak. And we will ask ourselves, if that happens, how does the flow change across the expansion wave? And how is this process different from what happens across a shock wave? apart from fast expansion, fast compression, if that is it. Having learnt about both shock waves and expansion waves, we will put together all that we have learnt and ask ourselves, what if both of them formed in a supersonic flow? For example, what if we had a diamond-shaped aerofoil meant for the wings of a supersonic aircraft? Then we could expect shock waves in some places, expansion waves in others, and with the corresponding increases or decreases in pressure, we may expect lift or drag. And the question is, how do we predict those? So far, we have talked about external flow for the most part. What about an internal flow? It would seem that if the cross section varies, as in a nozzle or a diffuser, then obviously the flow is three-dimensional, but perhaps we may yet approximate it as something close to a one-dimensional flow. When is that? And as a flow expands through a nozzle, what happens to it? Is there a chance that a shock wave will form or an expansion wave? What about for flow through a diffuser? And what if the internal flow is through a duct of constant cross section? Yes, surely we can treat that flow as one-dimensional, but what if viscosity became significant? What if heat transfer became significant? How do we account for those? And yes, I do mean to say that for the most part, we will not be accounting for the effect of viscosity in this course. We will be treating the flow as inviscid mostly. Does that mean there is no boundary layer? There is a boundary layer. It's just that that's a subject for a more advanced course. The same goes for the effect of heat transfer. For the most part, we will be regarding the flows we study as adiabatic. For this course, we will be using the textbooks by Professor John D. Anderson, Modern Compressible Flow with Historical Perspective, and by Professor E. Radhakrishnan, Gas Dynamics. Now, Professor Anderson has also written a textbook on aerodynamics. If you have a copy, by all means use it, because a lot of the topics for this course may be found in both his books. Not surprising, because a lot of the early research on compressible flow was conducted by aerospace engineers. You may also be interested in looking up to online courses on gas dynamics by Dr. T. M. Muruganandam at IIT Madras, and on compressible flow by Professor Wesley Harris at MIT. First of all, we will see when we may treat a flow as one-dimensional and isentropic, and just as importantly, when we may not do so. Next, we will learn to appreciate how much the Mach number matters when we are studying compressible flow. We will see how a supersonic flow is affected by the formation of a shock wave or an expansion wave, or both. When the internal flow, that is in fact three-dimensional, may be treated as almost one dimensional and how we may do so. And finally, how we may account for the effect of viscosity or heat transfer in a pipe flow. I believe that learning about compressible flow will be more than informative or even interesting. I believe it will be quite enjoyable. I invite you to join me on this study.